This experiment is the basis of all electric motors. It shows you how, using just a magnet, in this case the compass needle here, and an electric current in this wire, you can produce movement. Now at the moment it's not connected up, so we won't have anything moving yet, but there is the magnet, the pointer of the compass, and the wire connected this end to the small cell. Mostly people call it a battery, but it's actually a cell, and there is a gap, so no current flows round the wire because there's a break in the circuit. But watch what happens to the pointer if I connect the wire to the end of the cell. Immediately the magnet, in this case the pointer, moves. Disconnect and it swings back. Connect again and it swings round. There is some interaction between the current and the magnetic field of the magnet. And what's happening is that the electric current, which is direct DC, that means current in one direction, produces a magnetic field round the wire there. And that interacts with the magnetic field of the pointer. You've produced movement from electricity and magnetism. In the last experiment, I showed you how a combination of a magnet and an electric current can give you movement, motion. Well, we're going to go one stage further now and see if we can make that motion give you a simple electric motor. So, I have a magnet, a very strong one. This is a neodymium magnet, and a screw. You can see that it really is very strong, and therefore the screw itself becomes magnetized. We have a simple 1.5 volt cell, and I'm going to put it so that the positive terminal is touching the end of the screw. And now I'm going to connect a piece of wire between the top, in other words the negative terminal of my cell, and the other end. I'm going to touch the neodymium magnet. I won't do it yet, but think what's going to happen as far as the electric current goes. Well, a current is going to flow through the screw, the magnet, along the wire and back into the negative terminal of the cell. So let's watch what happens to the magnet and to the screw when I touch it now. And you can see that slowly at first, and then it begins to speed up, and you've got a very, very effective little motor. If I take it away, the inertia of the magnet and the screw means it will carry on spinning. But just think about what's happening when I connect it up. Electric current flows from the positive terminal through the screw, through the magnet, and then through the wire and back along the wire to the negative terminal of the battery. Well, it's slowing down now, but let's just give it one more little burst to speed it up again. A very, very, very simple electric motor. Ready? Here it goes. And there it is at full speed again. This diagram shows our simple electric motor. It's in two parts, and we'll have a look first of all at the left-hand part. It shows the screw here, the neodymium magnet and the connecting lead, and it also shows the magnetic field of the magnet, which is vertical, and the direction of the current, which is across from the screw, that arrow there, to the connecting lead. There's a further arrow, this black one, and that shows the direction of rotation of the magnet and therefore the screw as well. And notice that this is tangential to the magnet. On the right here we have a view of the whole motor, and this also shows you the battery, or strictly speaking the cell, the screw, the magnet and the piece of connecting wire. And it is because of the interaction between the current and the magnetic field that the motor spins. In the latter part of the 19th century, the British physicist and engineer Sir John Ambrose Fleming came up with a very simple way of remembering the directions of the actions of the motor effect. So, using your left hand, remember left hand, the first finger, that one, represents the direction of the field, the magnetic field. At right angles to it, the second finger, the C in the second finger, represents the current. And right angles to both of these, the thumb represents the direction of the motion. So field, that's the first finger, current, second finger, thumb, motion, and you see they're all at right angles to each other. And that is known as Fleming's left hand rule. Now we've considered Fleming's left hand rule, we can see how this applies to our simple motor. And if you look at the diagram, you can see that the field, the blue arrow there, is vertical, and the field is represented in Fleming's left hand rule by the first finger of your left hand. The current, the red arrow, which is at right angles to the field. Remember that this drawing is a 2D version representing a 3D situation. So current represented by the second finger of your left hand, and finally the third arrow, the black arrow, the motion, which is represented by the thumb of your left hand, and the motion is the rotation of the magnet about the vertical axis here. Field, current, motion, all of them are at right angles to each other as specified by Fleming's left hand rule.